Hey, my amazing Math 205 students. I hope that you guys are having a wonderful weekend. This lecture is for Monday. I just so wish you were up here with me. I miss my class. I miss being with you. I miss being able to hear your questions and see your faces. I just wish that I could test and just give you out tests and have you return them. I just miss class. I'm praying everybody's well and that all your families are well. Okay, today's lecture. Today's lecture I think will be reasonably short. We're in 5.5. We kind of finished up 5.4. The exponential function e to the x. And so what I wanted to do is I wanted to gather for you guys, collect, put it into a basket, kind of the properties that we've shown. So in case you don't have them, what you can do right now is just stop. These I think we've made most of them flashcards, but what I want you to do is just write those down. So just pause the video. Hopefully it's not too late, so that you can just write those down. So write down those 10 properties that we've shown for the exponential function, and I'll just wait. Okay, I guess that probably took about 5 minutes, 6 minutes, maybe a little bit longer. But I wanted them to be in your notes as we start heading towards our quiz, which is going to be on Friday during class time. And reminder, what homework is in that? That is section 4.4, 4.2. Okay, that's global maxes, global mins. 4.2 is concavity, and then 5.4. I think I'm going to restrict it to part 1. There were 2 parts of the homework, so it's going to be 5.4 part 1 only. I hope you guys are getting. I hope. I mean, I'm so sorry you have to watch me like this. I hope you're getting things from these videos. I hope that it's just not just a horrible teaching experience for you guys. Okay, so here's a theorem that's important, and I guess here's your homework. I'll send it out in an email also, but in case you wanted to get started on it. This is homework 5.5. I assigned problems 1, 5, 11, 13, 15, 23, 27, 31, 37, 53, and 55. Okay, this is going to be related to logarithms. This is going to be related to logarithms. Okay, and that's what we're heading towards. This is an important function. This is an important theorem. Okay, you can read it, and then I will read it. So go ahead, read it out loud, and then I will read it. Okay, it says here, if f is a strictly increasing function. Okay, now remember, the definition of increasing is kind of a pain. It's that x1 is less than x2 implies f of x1 is less than f of x2. Not an easy definition to show. However, we showed that if the derivatives are always positive, it means the function's increasing. Now what this theorem says is that if a function's strictly increasing, then the function has an inverse function. And we want inverse functions. Inverse functions are like Control Z, okay, on a Windows machine, or Apple Z. It undoes. I mean, how many times in relationships do we wish we had a Control Z? How many times have you said something in a relationship where you're like, well, I wish I could probably take that back, okay? Or how many times in life, like when you're blowing by a policeman going 20 miles an hour over the speed limit, how many of us wish we had an inverse function at that point in time to undo what we just did, okay? And that's a really, really useful tool. And this theorem says, as long as your function's strictly increasing, you'll have an inverse function. There's a parallel, a sister. These come as twins. There's a sister one that says that if f is strictly decreasing, then it also has an inverse. So if your function's always going up or your function's always going down, then you know that you're going to have an inverse function. Now let's try to remember from high school what an inverse function does. It undoes what a function does. So I'm just going to use not even numbers. Suppose I have a function, I'll say it sends apple over here to smiley face. Okay, so I have a function that sends apple from the domain to smiley face in the range. Well, what the inverse function does, the inverse function can undo this, and it takes smiley face and sends it back to apple. I mean, it's kind of like there was a bus that used to take you, okay, unless you were privileged, okay, like my youngest daughter. The older four just are so angry because we drove the youngest to school every day. The rest of them had to ride the bus to go to school. Okay, but so there's a bus that takes you to school. But how many people are happy at the end of the day that there's another bus that takes you back home? Okay, and that's what an inverse function does. An inverse function can undo what a function does. Like, for example, if we're dealing with numbers, if we have f of 2 is 7, then f inverse of 7 is 2. It undoes what the function does. It's like the control z for this function. Okay, now there's two, we're not going to spend time talking about inverse functions. The domain of the inverse function is clearly the range of the original function. Say that. Okay, now say it again. The domain of the inverse function is the range of the original function. Okay, now there's two just really important properties related. I always get my head cut off in these videos. Okay, there's two really important relationships for inverse functions. And it's not hard. It's a bit of a shell game. You feel like you're at the beach and they're saying, you know, follow the pebble, and you got these shells there. Okay, but if you just pay attention, you'll be able to see it with me. Okay, so if f sends apple to smiley face, and f inverse of smiley face is apple, one of the relationships is this. F, now I'm not going to put in the apple. I'm not going to put the apple here. Well, I guess I've got a marker. You don't, okay? But I've got a marker. F of apple is smiley face. But f inverse of smiley face is apple. So if I put this, I just drive that like a Toyota pickup truck in for that apple there, I can see one of the two important relationships between a function and an inverse function. Okay, so I'm just going to substitute this in here. I'm just going to write this thing and put it in there. So I would have f of apple, but apple is f inverse of smiley face. F of apple is smiley face. Okay? So this is one of the key things. Okay? The function, if f inverse sends smiley face to apple, the function undoes what the inverse function does. They can just undo each other. Okay? So this says f of f inverse of smiley face just takes you back to smiley face. Just takes you back to smiley face. The other one's just as simple. The other one's just as simple to get at. If I just erase this, okay, and then if I look here, I know that f inverse of smiley face is apple. So this is my first relationship. Okay, we should probably put it in a box. I'm going to put X's where the smiley face. Don't worry about the variables here. Okay, f inverse of smiley face is apple, but smiley face is f of apple. So in this case, I'm going to drive this like a Land Cruiser in for smiley face and just substitute it in there. Since smiley face is equal to this, then I would have that f inverse of f of apple is equal to apple. And that's what we're saying. The inverse function can undo what the function does. And this is the second major relationship that you have relating the function and its inverse function. Now here's the thing, because typically most of the time we have x as kind of like the domain variable. In both of these locations, in both of these formulas, I'm going to use x. But we got to be a little bit careful. So in my first major, so this would be a flashcard. This is the front. This is the back. F of f inverse of x equals. That's what you write down. F of f inverse of x equals. F of f inverse of smiley face. F of f inverse of x is equal to, and on the back you put x. F of f inverse of x is x. And the other one is this. Now in this case, the x is coming from the domain of the inverse function. F inverse of f of x is also x. But in this case, the x is coming from the domain of the original function. Okay? These are two really important formulas. And we're going to need one of them, possibly both of them, today. So f of f inverse of x is equal to x, and f inverse of f of x is equal to x. So write those down. Write those down. Okay, write those down while I erase the board. Okay. Now, I didn't erase one of the lines here. I didn't erase two of them, clearly. I didn't erase 9. I should have erased 10. I'm not even speaking English, am I? Okay, sorry. Okay. E to the x is always increasing, and it's always concave up. So its graph looks like this. It's always positive. It goes through 1. It's always increasing, and always concave up. This is the graph of e to the x. But because it's always increasing, this theorem guarantees there must exist an inverse function. This theorem guarantees there must exist an inverse function. Okay, so that would mean there's a function that can undo e to the x. Like, for example, and I guess maybe I'll call it, if e sends x, and I guess I don't know exactly what variable I'll use. I guess I'll use ice cream cone. If e sends x to ice cream cone, again, it's always increasing, so it has to have an inverse. Instead of using this notation for its inverse, I'm going to use this notation because this is, in fact, the inverse of e to the x. Okay, this is the inverse of e to the x. The natural log function that you learned about in high school also, but you probably didn't pick up on, the natural log function is the inverse function of e to the x. So if e sends x to ice cream cone, the natural log is going to send ice cream cone back to x. Okay, and so if we're looking at these two identities, this one would say e to the x is equal to ice cream cone, but x is equal to the natural log of, x is equal to the natural log of ice cream cone, so this would be e to the natural log of ice cream cone is equal to ice cream cone. So this is this identity. That's that identity right there in terms of E and its inverse function. Now typically we wouldn't write it with an ice cream cone variable. Typically it's written like this. Typically it's written like that, e to the natural log of x. The other one, which is the second one, looks like this. The natural log of ice cream cone, and I'll go all the way over here, is x. The natural log of ice cream cone is x, but ice cream cone is e to the x. And so we have this second identity. We have the second identity right here, that the natural log of e to the x is x, and e to the natural log of x is x. So write those down, write those down, write those down right now. Write those down, okay? These are essentially these two major properties related to the natural log and its inverse e to the x, and e to the x and its inverse natural log. Okay, so let me now get rid of all this. I know I said write it down, but you can pause me. I guess in class you can't. That's maybe the only advantage. The only advantage to teaching online versus for learning online versus learning in the classroom, I think, is you can pause me, okay? And you can watch me whenever you want, which is probably never, wanting to watch me. Okay, so let me put these up here. E to the natural log of x is x, okay? And then the other one I'll just kind of slide over here. The natural log of e to the x is x. And this is just the fact that they're inverse functions of each other. Okay, now I want you to remember this flashcard. Okay, take the derivative of that. Take the derivative of that. Let's see if you've got that down. Take the derivative of it. Go ahead. What's the derivative of e raised to any function? What's the derivative of e raised to any function? Go ahead, write it down. Write it down. Now this is when I wish I could say cheat. Look off somebody else. See if you've got the same flashcard that somebody else has. And if you've got nothing, then you better find something. Okay? And I can give you a hint. Go back and look at those 10 properties. Go back and look at those 10 properties. Okay, now you can cheat off me. It's just e to the f of x times f prime of x. This was one of our flashcards. This is one of our flashcards. Now, I'm going to take this identity that just relates, I know you're not listening. I could say whatever. That just relates hamburgers to hot dogs, okay? That just relates the inverse functions of e to the x and its inverse natural log of x. And what I'm going to do is I'm just going to take the derivative of both sides. Remember? Two kids come complaining. What do? All right, it's okay to spank one side with the derivative, provided you spank the other side with the derivative. Okay, now, this would logically follow from this. Okay, now, who wants the derivative on the right? Who wants the derivative on the right? How many people think they can maybe figure out what the derivative on the right is? What's the derivative of x? Now, hopefully, especially with a quiz coming up, everybody's like, we own that one, Dr. Warren. Now, let's look at the derivative of this. This is set up exactly like e to the f of x. But who's the f of x? Who's the f of x? Who's the f of x? Well, if you look here, my f of x is the natural log of x. So just using this flashcard, this is going to be e to the f of x. You're like, Dr. Warren, you didn't write down f of x. I know, this is the f of x times the derivative of the f of x. Like, Dr. Warren, where are you going with this? Where are you going with this? Well, just wait. But up here, e to the natural log of x is equal to, say it. E to the natural log of x is equal to x, so I can substitute that in here. E to the natural log of x is equal to x, so this is x times the natural derivative of the natural log is equal to 1. But this would imply that the derivative of the natural log of x is equal to 1 over x. The derivative of the natural log of x is equal to 1 over x. How sweet is that? How sweet is that? Okay, we just used the basic property of relating exponential functions to their inverse, the natural log. We took the derivative of both sides, and lo and behold, without any work whatsoever, we get the derivative of the natural log. Okay, so that is definitely a flashcard. That is definitely a flashcard. Okay, we've got that. Flashcard, here's my front. The derivative of the natural log of x. Here's my back. 1 over x and 1 over x. The derivative of the natural log of x is equal to 1 over x. I'll let you write that down. You can pause and write that down. In fact, I'll write it down with you. Okay, now I've got to talk a little bit about domain and range for the natural log. Remember, e to the x looks like this. Really, the only value we know immediately, we know e sends 0 to 1. We know e sends 0 to 1. Okay, e of 0 is 1. Now remember, since natural log is e to the x's inverse, the natural log's job is to pick up this child at school and take him back to 0 at home. Since e sends 0 to 1, natural log's going to send 1 back home to 0. So the natural log, if this is e to the x, the natural log of 1 is 0. Now remember back in high school that the inverse functions reflect, half of you like, Dr. Warren, I remember nothing. I remember nothing from high school. Okay, remember back in high school that the inverse functions reflect over the line y equals x. Their graphs reflect over the line y equals x. Okay, since this goes like this, the natural log is going to follow the distance. If I take a perpendicular line from here to here, that distance is equal to that distance. You might remember doing that. And this keeps going like this. But the domain of e to the x, is everybody. It's all real numbers. However, the domain of the natural log function is just from 0 to infinity, and there's nobody at 0. This is a vertical asymptote. And so we don't really have to worry about the division by 0. We don't have to worry about division by 0 that shows up in the derivative. Okay? Natural log is not defined for negative values or 0. Say that. Natural log's not, it doesn't really, it's not that important for what we're doing in 205, but it's something that I felt like you needed to know. Okay, so okay, let's see if you can remember this. Let me make sure I'm doing this the right way. Okay, yeah. Okay. Now remember, e and natural log are inverse functions of each other. That's right, there is English. Are inverse functions of each other. So look at those identities, and then try to see if you can't guess what e to the natural log of heart would be equal to. Go ahead, write it down. What do you think it's equal to? What would you guess? e to the natural log of heart, what do you think it would be equal to? Go ahead, look at the identities and write down what you think it is. What'd you say? Did you say heart? Then you're right. E to the natural log of anything is itself. So e to the natural log, now I'm going to change that heart to an f of x, then e to the natural log of f of x would be equal to f of x. E to the natural log of f of x would be equal to f of x. Right? We're just using the properties of the inverse functions. Okay, now what I'm going to do is I'm going to do the exact same thing, but it's just going to be a little bit more complicated. I'm going to take the derivative of this side, which is perfectly okay, provided I take the derivative of the other side. I'm spanking this side with the derivative, which is okay because of the equality. It's equal to the derivative of the other side. Now this one's a little bit more complicated. And I probably should have picked a different function other than f, but I kind of want it to be f. Let's just say I've got e to the g of x. What's the derivative of e to the g of x? What is the derivative of e to the g of x? Use that flashcard, because you're going to need it on Friday. What's the derivative of e to the g of x? And hopefully you said, Dr. Warren, all we do is write this thing down. All we do is write that thing down, and then take the derivative of that, and then take the derivative of that. Okay, so that's what I'm going to do. This is my g of x. This guy right here, that's my g of x. So taking the derivative of this, it would be e to the natural log of f of x times the derivative of g of x. Dr. Warren, that's not g of x. Okay. The derivative of natural log of f of x would be equal to f prime of x. So all I'm using is our chain rule for the exponential to do this here. So now I've got this is equal to this. Now I'm doing the exact same thing again. It's a sleight of hands. Let's look at that. E to the natural log of f of x is f of x. Well, here's an e to the natural log of f of x. I better put some imply signs in here. Then this would imply that f of x times the derivative of the natural log of f of x is equal to f prime of x. Now let's get out of Vietnam. Let's get out of Vietnam and go back and we started with this, just fundamental property of inverse functions. E to the natural log of anything is that thing. Replaced this with the f of x, took the derivative of both sides, used a property we derived the other day, then just substituted this in for that. And so if I get this guy all by itself, I just got to divide by that guy. This guy needs to go away. He needs to come under here. So I get that the natural log of f of x's derivative is just the derivative of f divided by f of x. And this is a flashcard. That is a flashcard. So those are the two major flashcards for the day. This is a flashcard and that's a flashcard. I'll just put this up here. That's a flashcard and that's a flashcard. Okay, so on your flashcard it would look like this. Here would be your front, here would be your back. You would have the natural log of f of x prime, and on the back you would have f prime of x over f of x. But there's nothing, you're like, Dr. Warren, there's so much, this is so hard. No, it's just a lot of symbols, guys. It's just a lot of symbols. The exponential function, you got the e and the exponent, you're like, oh, it's way too hard. But not really. It's not really that hard. It's really not that hard. Okay, now what I want to do is I just want to look at some problems that would match up well with some of the ones that we have here. So there isn't a ton of theory in this section until we start deriving some more properties of the natural log function. Okay, but that's not for tonight. That's not for tonight. So let me give myself some board space here. Now my first problem that I want to look at is going to be in this section 5.5. It's not your homework problem. It's not a homework problem. It's homework. It's problem number 12. It's exercise number 12. So you can even open the book if you want, and then look at that exercise. Now what they have here is they're asking us. I'm going to change. They say G. They say F. I'm going to say G. They give us this function. They give us this function. It's natural log. It's natural log of 3x squared minus 3x plus 1. And what they want us to do is find the derivative of this function. Like, Dr. One will never do this. We'll never be able to do this. And I'm going to show you that you're going to have no problems with this. You're going to have no problems with this. The derivative of this would be the derivative of that. Let's use this flashcard we just derived. The derivative of natural log of a function, the derivative of natural log of a function, so this is my f of x. That's my f of x right there. Just using this flashcard would be the derivative of f of x. It's a squared. The derivative of that. Now here you don't even need to think. It's almost kind of like with quotient rule, where you just write down that denominator squared. Here you just write the function down again. There's no differentiation. You're just copying. Now can you take the derivative of that? Can you take the derivative of that? And hopefully you're like, yeah, I can take the derivative of that now. It'd be 6x minus 3 over 3x squared minus 3x plus 1. See, you can do it. See, you can do it. Okay, it's not that bad. It's not that bad. So there's the first exercise. The next exercise is exercise 29. I guess there's exercise 12. Now here they're asking. Ooh, this looks nasty. This looks nasty. Okay, they've got a function g of x equal to x squared times the natural log of e to the 2x plus 1. Woo! Okay, and what they want us to do is find the derivative of this. Okay, now the first thing you need to do is not treat this like a McDonald's drive-thru. Okay, this is not something you're just going to drive up through and immediately get it handed to you. All right, you're going to have to sit back and take your time with this, or else you're going to mess it up. But look at me. None of this is hard. There's not a single step of this that's hard, as long as you have your flashcards. As long as you have your flashcards down. Okay? The first thing I run into is that it's x squared times the natural log of e to the 2x. So we got to use product rule. We got to use product rule. It's this function times that function. So this would be, using product rule, the derivative of this guy times that guy. Do I do anything with that guy? Not now. Not now. You leave him alone. We're using product rule. Then there's a big plus sign. Then there's a big plus sign. Then the derivative of the first, the derivative of the first times the second plus the first times the derivative of the second. So this was just product rule. PR. Product rule. Are we done? No, we're not done. We still have derivatives to take. Now, how many people think they can take? How many people can take that one? How many people are like, I got that one before you, Dr. Warren? What is the derivative of x squared? Did you say 2x? You're right. Oops. I don't want that to look like that's up there. Plus 1. So we're done with this part. This part we ain't done with. Okay, now we've got the natural log of e to the 2x plus 1. Dr. 1, I'm never going to be able to take the derivative of that. Okay, let's just use our flashcard that we derived. My function f of x is all of that crap, e to the 2x plus 1. So just using that flashcard, the derivative of this is going to be 1 f prime of x over f of x. Say that. F prime of x over f of x. This is my f of x. All of this is my f of x. So it's going to be the derivative of e to the 2x plus 1 over e to the 2x plus 1. Now, Dr. Warren, we're done. No, we're not done. This is done. I agree. This ain't done because we still need the derivative of this. Oh, Dr. Warren, how about that? That's done. That's done. That's done. This ain't done. Now here, we're going to need another flashcard. We've already written it down once. What's the derivative of e to any function? Remember, it's just e to that function times f prime of x. So using that, this is just scribing. Right now, I'm wondering what I'm going to eat for dinner tonight. I'm not thinking at all. This guy, just writing it down, no work to do there. Done. Okay, what's the derivative of the 1? What's the derivative of the 1? Okay, so that's 0. Now let's take the derivative of this. Using that, oh my gosh, I can't believe that I'm that out of shape. Okay. It's e to the f of x, taking the derivative of this, it's e to the 2x times the derivative of 2x, times the derivative of 2x. But what is the derivative of 2x? What is the derivative of 2x? And hopefully, like Dr. Warren, that is 2. So I have an eraser, you don't. Sorry. And there we're done. The derivative, we're done taking the derivatives. At this point in time, you don't need to simplify. If all I ask you to do is take the derivative, I want you using your valuable time on a test or a quiz, moving on to another question, not simplifying this to match some answer in the back of the book, okay? You've done it right, you've done it right. This is the problem. 50% of the students will not recognize here, you gotta start with PR. You gotta start with PR, okay? Just like any good business, it starts with PR. It starts with PR, and a good idea, Calculus is a good idea. Calculus is a good idea. Okay, so there's an example that's a little bit more involved than the one above it. And at the beginning of the day, you would have been like, Dr. Warren, I'll never understand this. But now you kind of do. If you admit it, now you kind of do. Okay, let's look at another example. Okay, this is problem number 55. This is problem number 55. So let me get rid of this guy. And I want to give you guys an assignment here in just a second. Here's 55. It says this: find the equation of the tangent line at the point 2 natural log of 4. The moment you see that, you're like, this problem's going to suck. The moment you see that, you're like, this problem's going to suck. Okay. The tangent line at the point 2 natural log of 4 to the function f of x equals the natural log of x squared. And you're like, Dr. Warren, as far as the function's concerned, this looks a lot simpler. Okay? But this is the problem. I'm asking for tangent line. When I say tangent line in this class, bing! You write down what? When you see tangent line, when you hear tangent line, when you read tangent line, what's the first thing you write down? Write it down. Write it down. Okay, now I'm going to write it down. Now, if you're not taking notes, if you're just watching me and you're not taking notes, it's going to hurt later. It's going to hurt later. It's like not running wind sprints when you should be, if you're an athlete. It's conditioning. And hopefully, like, I own that, Dr. Warren. I've written it down so many times. Y minus f of c equals f prime of c times x minus c. Okay, now looking up here, who's the c? Who's the c? And hopefully you're like, Dr. Warren, you've trained me well. This ends up being the c, and that's the f of c. That's the c, and that's the f of c. Now let's just make sure it's right, okay? Here's my function. F of 2 better be the natural log of 4. Well, wherever I see the x, I'm putting a 2. And I see it is in fact the natural log of 4. Now let's just plug that information right in. Let's just plug the c in here. So the first thing I would do, so I don't make a mistake, I find my c, and I just put that in. The next, if they give me to it in point form, then I know that that's just the natural log of 4 in this case. If they don't give it to me, then I know I have to plug the c in there. But again, that's not real hard. Like Dr. Warren, I don't like the natural log of 4. It's just a number. It's just a number. So now I'm there. Now I'm there. Am I done? Am I done? And of course, you're like, no. You still need to find the slope. You still need to find f prime of 2. So let me get rid of this exercise. So there's your function. You take the derivative of that. I can't do it. Yes, you can. Use your flashcards. What's the derivative? What's the derivative of the natural log of x squared? Just go ahead. Dr. Warren, I don't even know where to start. Who's the f of x? Who's the f of x? So go ahead, take that derivative. Okay, you can pause it if you're not sure what you're doing, and then now I'm going to do it, but you do it first. Using my flashcard, it's going to be 1, it's going to be the derivative of x squared divided by x squared. But the derivative of x squared is 2x over x squared. Now just cleaning this up a little bit, this is going to be 2 over x. That's going to be 2 over x. So Dr. Warren, what I do is I put the 2 over x in here. No, that's not what you do. What you do is you put in f prime of 2. So you don't put this in here. It would look nothing like a line. It would look nothing like a line. Where you see the x, you put a 2. And lo and behold, we find out that the slope of the line is 1. We find out that the slope of the line is 1. So then the equation of my tangent line is just that point slope formula of that line. Dr. Warren, I don't like the natural log of 4. It's just a number. Get out a calculator. Calculate it. You'll see it's just a number. Don't let it bother you. Don't let it bother you. So the equation of the tangent line at the point 2 natural log of 4 to the function f of x squared is that. Now the book, the answer in the back of the book, they may take this guy to the other side, they may simplify it, but I like the point slope formula of the line. Okay, just one more exercise. Then I'm letting you go. All right? One more example. This one's going to be a little harder. Oh, thanks, Dr. Warren. This is exercise, I guess, 56. Okay. We've got this function. We got this function, f of x equals the natural log of x. And Dr. Warren, what we have to do is take the derivative of it. It's a little bit more. It's asking, when is this function increasing? on the domain of the natural log function 0 to infinity. When is that function increasing? When is it increasing on the domain 0 to infinity of the natural log function? We want to avoid 0, okay? It's not defined here, and certainly not defined there. Okay, now, as we get ready for our third test, now, how do I determine when a function's increasing? What do I do? And did you say you find the critical points, Dr. Warren? Then you create a sign chart for the first derivative. That's right, that's right. So how do I find critical points? Like, well, Dr. Warren, you take the derivative of it and you set it equal to 0. So let's take the derivative of this. And f prime of x would be the derivative of that. What flashcard do you use for that? Which flashcard do you use for that? You want to take the derivative of this. You're like, Dr. Warren, you just take the derivative of the numerator and you take the derivative of the denominator. No, that's not what you do. You know better than that. You use quotient rule. This would be equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Like, Dr. Warren, why are you writing that down? That's so simple. I know. For some people, I just want to have their notes nice and clean. Okay, now, how many people can take the derivative of that? So let's put this over here. 1. Now, how many people can take the derivative of the natural log of x? I've forgotten, Dr. Warren, I forgot what it is. Well, fortunately, we wrote it down here as a flashcard. The derivative of the natural log of x is 1 over x. So the derivative of this guy is 1 over x. Are we done? Unfortunately not. We're not asking what's the derivative. We're asking when's it increasing. And now it's a fraction. So we've got to actually sweep this mess up a little bit. And I guess I'll come over here, because I'm already here. This times this is 1. Okay. Now I'm looking for critical points. Like, Dr. Warren, it's a fraction, and there's a natural log in it. Well, remember, my critical points are where f prime equals 0, or f prime does not exist, but it's in the domain. Well, the only place the derivative is not going to exist is 0, okay, but 0 is not allowed in, okay, and when this is negative, but it's not allowed in. So there isn't any of those kinds of critical points. You got to be at JMU to be in the JMU sororities or fraternities, okay? This is not, 0 is not a critical point because it's not a JMU student. Okay, now the other type are when the derivative is equal to 0. But once again, if you've got a fraction that's equal to 0, this is like the third time I've said it, the only way a fraction can be 0 is if which part's 0? Dr. Warren, the numerator. So if I wanted my fraction to be 0, I would want that numerator to be equal to 0. You're like, Dr. Warren, could you graph the natural log for me again? Yeah. This is e to the x. That's the natural log. Okay, so I'm asking, when will the natural log of x be equal to 1? When will the natural log of x be equal to 1? You're like, I don't know. So if I take that guy here, I would get that. And you're like, okay, Dr. Warren, but I want to figure out what value of x would give me 1. If I could only get at that x, but Dr. Warren, it's inside the natural log. How could I possibly get at it? How could I possibly undo it? And hopefully you're like, wait, natural log has an inverse function. If natural log sends x to 1, then natural log's inverse, e, has to send 1 back to x. If natural log sends x to 1, since e's the inverse, then e sends 1 back to x. And we see here that we found x. X is e to the 1. And you're like, Dr. Warren, what's e to the 1? It's just e. What's e? Well, that 2.71, blah, 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 blah. It's an irrational number. It's an irrational number. But it doesn't matter. It doesn't matter what e is. What matters is this helps us answer the question, when is this increasing? Now remember, my domain is from here to here. We're not worried about that at all. Now we're looking for places where the derivative is 0, but the only time that's going to be 0 is when x is e, which is like 2.71. So the only way the derivative can be 0 is there. That's the only 0, more importantly. So now all I've got to do is test. Okay, so now let's pick a number. Let's pick a number that's bigger than e. Like a trillion. Okay? If I put a trillion in here, natural log of a trillion is definitely going to be bigger than 1. This grows slowly, but it's definitely going to be bigger than 1. Okay? Okay, so I would have 1 minus something that's bigger than 1 over a trillion squared, but you're squaring, so it's positive. Okay? So the only thing I'm concerned about is the sign. 1 minus the natural log of that. This would be negative if I'm putting a trillion in, divided by a trillion squared, which would be a negative divided by a positive, which would mean I'm negative over in here, which means I'm decreasing. Now let's take a number that's less than e, like 1. The natural log of 1 is 0. So putting 1 in here, I get 0. This would be positive. Okay, 1 squared is positive. Remember, I'm putting 1 in. So I have a positive over a positive. I'm positive in here. Which again, our theorem tells us then we're increasing. So if we're looking for intervals of increase, if we're answering the question, when's it increasing, we almost always want closed intervals with increase and decrease, but in this case, 0 is not in the domain. But e is. So I'm increasing on 0 to e, and I'm decreasing from e to infinity. Okay, so here's some examples related to the natural log function. And here's some homework for that. Now what we're going to do next time is we're going to spend just a little bit more time. Developing some properties, kind of like those 10 properties, that we had for e to the x, but for the natural log. And then we're going to start, calculus is about what again, guys? Calculus is about limits, derivatives, and integrals. We've talked about limits, we've talked about derivatives, we're going to start integrals. Our last major topic, and it's going to take us a while, our last major topic of the semester. Okay, I hope you got some things out of this. If not, send me some email. I may try to set up some Zoom office hours this week. All right, thanks guys.